Hello everyone. Today we shall discuss about irrational numbers. We saw in the previous section that there may be numbers on the number line that are not rationals. In this section, we are going to investigate these numbers. So far, all the numbers we have come across are of the form p by q, where p and q are integers and q not equal to 0. So you may ask, are there numbers which are not of this form? There are indeed such numbers. The Pythagoreans in Greece, followers of the famous mathematician and philosopher Pythagoras, were the first to discover the numbers which were not rationals around 400 BC. These numbers are called irrational numbers or irrationals because they cannot be written in the form of a ratio of integers. There are many myths surrounding the discovery of irrational numbers by the Pythagorean Hipparchus of Croton. In all the myths, Hipparchus has an unfortunate end either for discovering that root 2 is irrational or for disclosing the secret about root 2 to people outside the secret Pythagorean sect. Let us formally define these numbers. A number S is called irrational if it cannot be written in the form p by q, where p and q are integers and q not equal to 0. You may already know that there are indefinitely many rationals. It turns out that there are infinitely many irrational numbers too. Some examples are root 2, root 3, root 15, pi, 0.0110111101111 dot. These are all irrational numbers. Remark: recall that when we use the symbol root, we assume that it is the positive square root of a number of the number. So root 4 equal to 2, though both 2 and minus 2 are square roots of 4. Some of the irrational numbers listed above are familiar to you. For example, you have already come across many of the square roots listed above and the number pi. The Pythagoreans proved that root 2 is irrational. Later in approximately 425 BC, Theodorus of Cyrene showed that root 3, root 5, root 6, root 7, root 10, root 11, root 12, root 13, root 14, root 15 and root 17 are also irrationals. Proofs of irrationality of root 2, root 3, root 5, etc. shall be discussed in class 10. As to pi, it was known to various cultures for thousands of years. It was proved to be irrational by Lambert and Legendre only in the late 1700s. In the next section, we will discuss why 0.01110111101110 and pi are irrational. Let us return to the questions raised at the end of the previous section. Remember the bag of rational numbers. If we now put all the irrational numbers into the bag, will there be any number left on the number line? The answer is no. It turns out that the collection of all rational numbers and irrational numbers together make up what we call the collection of real numbers, which is denoted by R. Therefore, a real number is either rational or irrational. So we can say that every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. This is why we call the number line the real number line. In the 80s, 70s, two German mathematicians, Cantor and Dedekind, showed that corresponding to every real number, there is a point on the real number line, and corresponding to every point on the number line, there exists a unique real number. Let us see how we can locate some of the irrational numbers on the number line. For example, locate root 2 on the number line. It is easy to see how the Greeks might have discovered root 2. Consider a square OABC with each side 1 unit in length, see figure 1.6. Then you can see by the Pythagorean theorem that OB is equal to 1 square plus 1 square, that is root 2. How do we represent root 2 on the number line? This is easy. Transfer figure 1.6 onto the number line, making sure that the vertex O coincides with 0. We have just seen that OB is equal to root 2. Using a compass with center O, a radius OB, draw an arc intersecting the number line at the point P. Then P corresponds to root 2 on the number line, right? Locate root 3 on the number line. Let us return to figure 1.7. Construct BD of unit length of perpendicular to OB. Then using the Pythagoras theorem, we see that OD is equal to OD, this one is the root 2 square plus 1 square, that is root 3. Using a compass with center O and radius OD, draw an arc which intersects the number line at the point Q. Then Q corresponds to root 3. In the same way, you can locate root n for any positive integer and after n minus 1 has been located, right? In this way, you can find various rational numbers and irrational numbers on the number line. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.